Hi, welcome back. This is your homework question. Let us solve this. This is the cantilever beam which is given in the question, and this is loaded with 2 point loads, one uniformly distributed load, one moment. First of all, let us label the points. Let this be the point A, this one be B, and this one be C. Let us start the shear force calculations. Coming to the point A, here only this 4 kilonewton is acting. The 4 kilonewton is acting in the downward direction. If we consider our section just left of A, the shear force at the point A will be FA is equal to positive 4 kilonewtons. Now coming to the point B. If we move our section to the point B, just right of B, we can write the shear force at the B, FB, is equal to this 4 kilonewton plus 2 kilonewton uniformly distributed load is acting for a distance of 4 meters. Therefore, the shear force at the point B will be equal to 5 kilonewtons. This is just right of the point B. Now coming to the just left, the shear force at the point B is equal to 4 plus this 2 multiplied with 4 plus 6 kilonewtons. On calculation, we obtain 18 kilonewtons. This much shear force is acting just left of the point B. Now coming to the point C. Between point C and B, there is no other loads. Therefore, the shear force at the point C will be equal to 18 kilonewtons. Now coming to the bending moment calculations. Bending moment at the point A, MA, is equal to this 3 kilonewton meter is acting in the anti-clockwise direction. So this causes a sagging moment. Therefore, this is considered as positive plus 3 kilonewton meter. Now coming to the point B. The bending moment at the point B is equal to this 4 kilonewton force causes a clockwise moment that is considered as negative. Why? Because it hogs. That moment will be hogging moment. Therefore, this 3 kilonewton meter negative 4 kilonewton multiplied with the perpendicular distance is of 4 meters negative. Then this uniformly distributed load is acting for a distance of 4 meters. Therefore, the total load is assumed to be acting at the center of gravity of this loading system. That is at the midpoint of this loading system. That will be at a distance of 2 meters from the point B and 2 meters from the point A. Therefore, the total load is 2 kilonewton acting for a distance of 4 meters multiplied with the perpendicular distance is 4 meters divided by 2. On calculation, we obtain the bending moment at the point B is equal to negative 29 kilonewton meter. Now coming to the point C. Bending moment at the point C is equal to this 3 kilonewton meter negative 4 kilonewton multiplied with the perpendicular distance is 4 meters plus 2 meters. Therefore, let us write 4 plus 2 itself minus this 2 kilonewton per meter acting for a distance of 4 meters, that is the total load, multiply with 4 divided by 2 plus 2 meters minus 6 kilonewton multiplied with the perpendicular distance is 2 meters. That is the distance between the point B and C. On calculation, we obtain the bending moment at the point C is equal to negative 65 kilonewton meter. Now let us draw the shear force diagram and bending moment diagram. Shear force at the point A is 4 kilonewtons. Let us say this is 4 kilonewton magnitude. Let us join these 2 points. Shear force at the point B, there are 2 points. One is 12 kilonewton, another one is 18 kilonewton. This is 4 kilonewton and let us say somewhere else here, this is 12 kilonewtons and this one is 18 kilonewtons. And that shear force at the C is also 18 kilonewtons. Why? Because there is no load at all. Between the point B and A, there is a uniformly distributed load. As a result, there will be a linear straight line like this. Then there will be a sudden rise here. Then there will be a horizontal line between the point B and A. Let us join this one with 0 magnitude. This entire area is positive area. Now let us shade this. From this we can find that what is the magnitude of a shear force at various points. This will be more useful in designing of any structural members and machine elements. Now let us draw the bending moment diagram. Bending moment at the point A is 3 kilonewton meter. This 3 kilonewton meter is a positive quantity. So we should be very careful in that. So this is positive, and bending moment at the point B is negative 29 kilonewton meters. Let us say somewhere else here. Between the point A and B, there is a uniformly distributed load. That is the only reason this shear force is a linear straight line. Whereas in the bending moment, it will be a parabolic curve. So we'll draw like this. It's a parabolic curve. And coming to the point C, it is negative 65 kilonewton meter. Let us say this is the point. Again, this will be a linear straight line. Let us join the 0 magnitude with negative 65 kilonewton meter. This entire area will be in the negative side. Let us join this also. Here, in the bending moment diagram, this portion is a positive quantity, whereas this portion is negative quantity. Now let us shade the area of the bending moment diagram. So here we find that some part of the beam is negative bending moment and some part of the beam is subjected to positive bending moment. Here there is a point. At this point, the bending moment is becoming 0. The sign convention of bending moment changes from positive to negative. This point, we call it as the point of contraflexure. Point of contraflexure is nothing but it is the point at which the bending moment becomes 0. Thank you.